Before I get started on announcements, if you look over here, there are some acids and some ions. Some of these are ones that we haven't looked at real commonly. Some are ones that people make common mistakes on. So take a minute, see if you can figure out the names of the ones where I gave you the formulas. The first two are acids because it has the H in front. The bottom one there has a charge that's going to have the ion name. And then on the right-hand side, we have mostly ions, and there's one that's a molecule. Okay, so H3PO4, what's the name of that acid? Phosphoric acid. So that's an acid that is found in sodas, the darker colored ones. Usually it's not found in like Sprite and 7-Up and stuff like that. H2CO3. Carbonic acid. So that's another one that's found in sodas. That comes from dissolving the carbon dioxide, the bubbles. Okay, so those are both acids. And then the next one, CrO4. I've got the Cr underlined because a lot of times when people see a C, they just jump right to carbon and assume that's what it's going to be. But that's not carbon. What is it? That is chromium. So this ion is named what? Chromate. Okay. So the other thing I see, so carbon, Cr, and then Cl shows up a lot in these ions. And a lot of times people mix up the chlorine with the carbon. So remember, if the next thing is lowercase, it's still part of the same molecule. So whenever you see a C, there are a lot of elements that start with C, double check. Another thing that was pretty common is for people to look at this and think I meant CI. It can happen, but it doesn't really ever happen. So you're never going to have carbon and iodine. Like, it's possible, but I'm never going to give you carbon and iodine together. So if you're not sure if it's an I or an L, it's an L. Okay, then over here we have perchlorate is ClO4, and the charge -1. So if you have trouble remembering the charges, that column with chlorine, bromine, and iodine, if they're monoatomic, they're -1. No matter how many oxygens you add, the whole ion is still -1. So if it's got chlorine in it, the ion's -1. If it's got bromine in it, the ion's -1. Okay. So this and this are very similar to one another. So even if you didn't have it memorized, you could kind of figure out what this one is because it mirrors this one. So what is it?
Mn.
Yeah, Mn for manganese. O4, and it is also -1. Okay, so those two go together. And then ammonium and ammonia get mixed up a lot. The IUM means that the ion behaves like a metal ion. So it's about the same size, charge density, chemically very, very similar to the sodium ion. And so that's why they put an IUM there, even though it doesn't have any metals in it. So what's the formula here? NH4 and the charge +1. So this is our only one on our list that is positive. There are a couple of other positive polyatomic ions. We're not going to worry about those. Oops, I forgot my 4. So this one is +1. Now, if it is ammonia, then we take away 1 hydrogen and it's NH3
with no charge.
with no charge.
Or neutral
And
charge.
this one is a gas, and so doesn't behave like a metal. So the top one here behaves kind of like a metal ion, but this does not behave like a metal at all. So looking at this, when we add a hydrogen to our ions, we make it neutral. And when we added a hydrogen here, we made it a positive charge. So what charge would you think just an H ion would have? +1. So you can kind of think of that when you're combining your ions to make an acid. every hydrogen you add cancels out one negative charge, okay? So if this was something that like, it just came to you, you knew it, you're in good shape. If you had to look these up or forgot what they were or were slow coming across them, definitely something to look at before your quiz. Now, I said the quiz was going to be on Friday, but there are a lot of teams that are out on Friday, and I just don't want to make up that many quizzes. So I'm moving the quiz to Monday. Hopefully we'll have fewer absences then. So Monday, the 25th. Now, what is on the quiz besides the ions? Yeah?
Ionic and covalent compounds.
No, we did have those on the test, so I'm not going to put naming the ionic and covalent compounds on there, but that's a good guess because since we were doing the naming the ions, okay? Definitely balancing equations. So if that's something that you are not quite getting the handle on, you can come to my office hours, or you can just, do a search on the internet for videos on balancing equations that'll walk you through it, or examples. And usually for people just doing several of them, at some point it clicks and it's like riding a bicycle. I get it. I'm not going to forget how to do it. Okay. But that's something you want to practice. And then did you have another one, or were you going to say balancing? Okay. Then the other thing I said was the stuff we've covered since the test. So one of those things was combustion analysis. I haven't decided if I'm going to put that on the test because it's not something that comes up a lot. It's good for critical thinking, but I'd rather focus more on the stuff in section 3.3, which is what we're going to go over today. So molarity, absolutely. Possibly combustion analysis. I will tell you for certain on Friday whether or not there will be combustion analysis. Okay, so those are things to know for your quiz. Now, since homework 9 was over the stuff we're talking about today, which is going to be on the quiz, I'm moving the due date on that because you have until Monday for the quiz. So I'm going to give you until Sunday to finish the homework assignment. So that got moved. And since that's part of chapter 3, I figured, well, I might as well move the vocabulary for chapter 4. So those are both due on Sunday. So I saw a handful of you have the vocab for chapter 4 in. Great. Thank you. I appreciate that. That's less homework for you over the weekend. But if you haven't done it yet, you've got a little bit more time. Okay. Questions? All right. So let's dive into molarity. So molarity is a way of looking at concentrations. Now, when we have looked at moles in sections 1 and 2, we've mostly been dealing with compounds. So compounds are pure substances. So since it is a pure substance, all of the mass is the same compound. And since all of the mass is the same compound, then we can just use the molar mass to find how many moles there are. So we say moles, mass, divided by molar weight. Now, in section 3, we're not dealing with pure compounds. What are we dealing with? What would you find the concentration of? Not a pure compound, but a solution. Okay, so which is a kind of mixture. So solutions some of the mass is the solvent. So the solvent is the thing that's doing the dissolving. We can have solutions of, say, metals. So we call those alloys, where we maybe have silver and gold mixed together. That's an alloy, okay? But for general chemistry, almost all the time, our solvent is not going to be a metal. It's not going to be an organic compound. It's almost always going to be water. So we call those aqueous solutions. So if I am looking at something that is an aqueous solution and I know the mass of it, I don't know how much of that mass belongs to the compound and how much of it belongs to the water. So I can't use that to find moles. All right, so for compound, a pure compound, I might write the mass. I might write 1.0 grams of HCl. Okay, so if I write grams, I'm implying that it is pure, that all of that mass belongs to the HCl. But for a solution, I might write something like 1.0 capital M. This capital M stands for molarity, and this is the concentration. And I still might write HCl. I'm putting the label of the solute, the compound. I don't put the water there. So I'm not saying HCl and water together. I just say HCl. But because I have that M, that means it is not all hydrochloric acid. Some of it is the water. Okay, so we need to be able to find the concentration of a solution in order to know how much is going to be our compound. So we're going to call the compound the solute. Okay, so that's whatever is dissolved in there. It's usually a solid. In the case of HCl, it's a gas. And so we can express our concentration in a few different ways. One common way to see it expressed is a mass percent. So we did mass percent for how much of an element is in a compound. We said how much hydrogen is in HCl, that kind of thing. We could also say how much, what percent of my whole solution is made up of the HCl. So this is really common commercially, meaning if you go to a store and you buy something, you might pick up the bottle and it would say on there that it is, your vinegar is 5% acetic acid, okay? If I have two liquids, sometimes I'll do my percents by volume. Again, it's just the ease of the manufacturer. I can measure 1 gallon of water, 1 gallon of isopropyl alcohol, dump them together. It's a 50-50 mixture, okay? So it's a lot easier for them to measure the volume or the mass of the things they're putting together. So this is also common commercially. And an example would be rubbing alcohol. So if you go into the pharmacy and you get some rubbing alcohol, it's going to say it's 70% alcohol by volume or 90% alcohol by volume. Okay. So that works really well for making things, but in chemistry, we want to know how they're going to react with one another. So we need to know how many moles there are. And this doesn't tell us how many moles. So instead, we use molarity. And that's most common in the lab. So it's pretty easy to measure the volume of something. And then this helps us to easily identify how many moles so we can do our calculations with that. There are some other kinds of concentrations discussed in section 4. We're not going to worry about those too much until next semester because this is the one you most commonly see in the lab. So since this M can appear on the bottles in the lab, if you pick up a bottle of hydrochloric acid in your lab, it might have an M on it. That stands for molarity. That's what you're going to see in the lab. Okay, so let's talk some more about molarity. So the calculation is the moles of the solute, which is what we call the thing we're dissolving, the compound, divided by the volume of the solution. Now, mass we talked about being conserved. So if I have 5 grams of one thing and 7 grams of another, I add them together, I'm going to get 12 grams. Not true with volumes. If I have 1 liter of water and 1 liter of isopropyl alcohol and I combine them, I'm not going to get exactly 2 liters. So when we say the volume, this is of not the water, but the whole thing mixed together. Now, if I am doing a problem and I say we use this much water, I'm just going to make the assumption that the volume of the solution is the same. But in your book and on active chemistry, it's going to have kind of awkward wording. It's going to say dissolved in enough water to make such and such volume of solution. That's why it says it that way. Okay, so we can write this as the formula M is equal to N over V. So M stands for molarity. N is moles, because too many things in chemistry start with M, so we picked a different letter. And then I'm going to put a little L next to the V. So this is a reminder that that volume should be in liters. You can just write V if you want, but when you're in lab, do you usually measure things in liters? No, this is about a liter. If this were all, say, water, this would be about a liter. Your tallest beaker is about this high, right? So you never work with as much as a liter, okay? But, so you work with milliliters. And so every time we do a calculation, we're gonna have to convert between milliliters, which is like this much, just the tip of your pinky, is going to be about a milliliter, or I like to say a miniature marshmallow. If you like mini marshmallows in your hot chocolate, that's about a milliliter. So there's about 1,000 of those, or I'm sorry, there's exactly 1,000 milliliters in 1 liter, about this volume, okay? So let's do a calculation. So if a salt solution has a volume of 250 milliliter and it contains 0.50 moles of sodium chloride, so that's our salt, what is the molarity of the solution? So we can just say molarity is equal to moles 0.500 moles divided by the volume, 250 milliliters. One thought there. But what's the problem?
We divide by liters, not milliliters.
Exactly. We need this in liters. So you can do one of two things. So the first way you could do this is you can say, I'm going to do unit analysis. So I'm going to multiply by a factor that's going to cancel that. So I'm going to multiply by something that has milliliters on top and liters on the bottom. That way my milliliters will cancel and I'll have liters. Okay. So milli means 1,000. So is the 1,000 going to go on top or on the bottom? Top. So I'm going to think to myself, are there 1,000 miniature marshmallows in 1 liter, or is there 1,000 liters in 1 miniature marshmallow?
1,000 mini marshmallows.
Yeah, so there's 1,000 mini marshmallows. So I'm going to put the 1,000 with my milliliters and the 1 down here. So I can plug that in and I would get 2.00 moles per liter. So our units on molarity are clearly moles per liter, but as we see in the label over there, sometimes instead of writing moles per liter, we just write the capital M. So if you see a capital M, that means moles per liter. Okay, so that's one way to do this. Another way to do this, once you're used to working between milliliters and liters, once you do this a lot, it's just going to automatically click for you how many liters it is. So your second way is to just convert
Milliliters to liters.
Convert the milliliters to liters. So the way that would look would be to say 250 milliliters times 1 liter over 1,000. That gives me 0.250 liters. And then I would do 0.500 moles divided by 0.25 liters, which is going to work out to that. Okay, so I plug this in. My calculator just gives me the number 2. There's nothing after the 2. It's just a 2. Why did I put extra zeros?
Certainty.
Certainty. So if I look back here, I have 3 digits that I know for my moles. And then this decimal point tells me I have 3 digits that I know for my milliliters. So I need 3 digits here. So you have to be smarter than your calculator. Your calculator just said, oh, everything else is a 0. I'm going to stop typing. You're going to say, no, no, 2 of those zeros are actually important. They're significant. So I'm going to write them. Okay. All right. Usually we don't go into the lab and just know what the moles are because there's no equipment that measures moles. We can go to the balance and measure the grams. We can go to the graduated cylinder and measure the milliliters, but we can't do that with moles. So we have to figure out how to find those moles. And finding moles depends on whether we're starting with the mass of the compound or the volume of the solution. So we're going to look at both ways. So if you're given the mass of the compound, you just do the thing we've always done. We have a mass, we're going to convert that to moles. Now remember that we need the molar mass, which sometimes we call the molar weight, MW, and sometimes we call the formula mass, FM. So since I use all of those terms, I'm going to try and, for the time being, say all of them so that you get used to that means the same thing, okay? So if I'm given the mass of the compound and I need the molar mass, what am I going to do? So let's say the molar weight is grams per mole. So that's grams is mass divided by moles. So if I want moles by itself, I'm going to rearrange this equation. So first I'm going to multiply both sides by moles, but then I have moles with the molar weight, so I would divide by the molar weight. So that's gonna give me, rearranging, moles equals mass divided by the molar weight. Okay. So this curly arrow just means I rearranged the equation. So if I have a problem where I'm given the mass, I can find moles. But if it's a solution, I probably also want to know the concentration. So I can find that concentration if I have the mass of the compound and the volume of the solution. Okay, so I'm going to have 3 steps. My first step is this. We've got to find our moles. And then I'm going to use those moles in order. Oh, sorry, I skipped a step. That was the second step. So first we have to find the molar weight of the solute or the compound. So usually we're not dealing with a pure element. So if I have a compound, I'm going to look at the periodic table and do what? Add together the masses of each of those elements. Okay, and then if I have more than one of an element, I have to add
them. Yeah.
It's so for
In
each
a
atom.
molecule, yeah.
All right. Then once I have the molar weight, I can do this step. And then finally, I do this step here, dividing the moles by the volume. So we're going to work through an example involving sugar. So table sugar has the chemical formula C12H22O11. It goes by the chemical name sucrose. Okay. So once you catch up on jotting down your notes, I want you to try and find the molar weight of carbon 12, hydrogen 22, oxygen 11. Okay, so C12H22O11. Does anybody think they have the molar mass?
Yes.
Mhm.
342.308.
That's about right.
Yeah.
So if you've got something slightly different, it probably depends on how many decimal places that you used. So if instead of 0.01 for the hydrogen, you use 0.0079, it would be a little bit less. I'm gonna round this to 0.31. You said 308, I'm gonna round it to
Yeah, fair.
0.31. Okay, and then that is in units of grams per mole. Okay, so here we have the question. A can of Mountain Dew, I looked this up online, is 355 milliliters and contains 46 grams of sugar, C12H22O11. What is the molarity or the concentration of the sugar? So our first step was to find the molar weight of the sugar. And that was 342.31 grams per mole. Now, our second step is to find the number of moles. So this is what we have always done as finding moles, is use our mass, the 46 grams, and the molar weight. Now, when we are doing calculations, we should start with the measured amount. How much is there? So the 46 grams tells us how much sugar. This is a ratio comparing the grams to the moles. So we want to start with how much is there, the 46. So this means we write it down first and it goes into the calculator first. There were a couple of people on the test who wrote it down correctly, but then put a different number into the calculator first. So since we're writing this first, we're going to put in the calculator first. We want to get rid of grams. We want to go to moles. This is per 1 mole. So the 342 is going to follow around that grams. And I plugged that in to get 0.13. Okay, now I have all kinds of digits here for my molar weight. Why am I only reporting 0.13?
Because the grams that you started with.
Exactly. So usually the measured amount is going to determine how many sig figs we use. And in this case, it does. There are only 2 sig figs here. So I can only report 2 significant figures. The 0 is not significant because it is to the left of the first non-zero. So we are not counting that. Okay.
It's still important though, right?
It is still important. It is
Yeah,
just not
Because
significant.
otherwise it would be 13.
Correct. Yeah, so we need the 0 and the decimal to tell us how big the number is. It just doesn't tell us how precise the number is.
Yeah.
Okay. And then our last step is to take our moles and plug it in with our volume to find our concentration. So molarity is going to be 0.13 moles of C12H22O11 divided by 355 milliliters, but we want our volume in liters. So we're going to do times 1,000 milliliters over 1 liter. So I plug this in and I get 0.37, and I can put capital M, or I can put 0.37 moles per liter. Either way is appropriate. Okay, so I have 37 with 2 digits here. Why doesn't this change the number of significant figures?
Because there's only one significant.
So that's what might make you think I should reduce it, right? But yes, this is an exact conversion.
Oh,
Okay, so when I go from one volume to another volume, from one mass to another mass, if I'm changing units like that, that doesn't affect my sig figs.
okay.
Yeah, because there are exactly 1,000.00000000000 on for infinity zeros per 1 liter. Okay, so exact conversion. All right, so that is our concentration of sugar in Mountain Dew. Now, I'm going to have you try and do the next problem a little bit more on your own, and we are going to switch beverages to a Starbucks Frappuccino. Because it's a little bit more consistent and because I can find the information online, I went with a glass bottle from the grocery store instead of a cup at the store. So a Starbucks Frappuccino, let's see, it is 281 milliliters. It's about 9.5 ounces. Contains 31 grams of sugar. Okay, so notice in this problem, I said, what is the concentration of sugar? I didn't actually put molarity. You'll find that's pretty common in chemistry, that if it asks for the concentration, we assume you know to find it in molarity, okay? So here, I put both molarity and concentration. Here, I just put concentration. Just know that you're looking for molarity, okay? You have already done step 1 because it's still sugar. So we've already got the molar weight. So now you're on to step 2, finding moles. All right, so to find moles, we've got 3 numbers here, the 281, the 31, and the 342. What did you work with? What did you do? So these 2 are amounts. One of them is the amount of the whole thing. One of them is the amount of just the sugar. So we want just the sugar, right?
Yeah.
So we're going to take the 31 grams.
Divided by the NW molecular weight.
Divide by the molecular weight. So our 342.31 grams on the bottom per 1 mole. Okay, so this is the same thing as dividing by the molecular weight. Our grams are going to cancel. And what did you get, AJ?
0.9.
Is there another 0 in there?
0.905.
Okay, 0.0905.
Yeah.
Okay. So this one's kind of tricky. We need to have 2 sig figs. Obviously, we have more than 2 digits here. Is this 0 significant?
No.
No, we all agree on that. Is this 0 significant?
No.
It is not. So some people look at that and they're like, but it's after the decimal. Our rule is it after the first non-zero? Is it after the rest of the number? Okay, so this 0 is to the left of the rest of the number. So these are not significant. Whereas these being to the left are the ones that we start counting. So this is our first one. This is our second one. Since the next digit is a 5, we can go either way, but the rule is to round down. So we would say 0.09.
Okay.
Okay. Again, if you were using a slightly different mass, you might have ended up with 0.091. Okay. So then we say our molarity is 0.090 moles divided by what?
0.281
Okay. And is that milliliters?
liters.
Liters. So you went ahead and converted to liters.
Yeah.
So if you didn't follow that, you took the 281 and divided that by 1,000.
Yeah.
To get the 0.281. Okay, and I get 0.332. And I can use capital M, I can use moles per liter. Okay, very briefly, part B. If you don't have the mass, you're probably being given both the volume and the concentration, because you're being given the volume, that's about 2 things. So you need to know what the concentration is. So you can find moles by taking molarity is equal to, let's do N over V. So if we want N by itself, we rearrange the equation and get molarity times volume in liters is equal to moles. Okay, so M times V gives us moles. So if I had, instead of 281 milliliters of this Frappuccino. Let's say I only had 100 milliliters and I wanted to find out my moles of sugar that I had. I can take my 0.32 moles per liter times my 0.100 liters. And that would tell me that I have 0.032 moles of sugar. Okay. So on Friday, we will talk about dilution problems. So take a look in your book, in section 3.3, it talks about how to do dilution problems. Take a look at that so you'll know what we're doing on Friday. Okay? Questions? All right. I will see most of you on Friday, except for the handful of people that I won't see until Monday.